first up to radiation pattern and power pattern, which effectively are distribution of electric field or the radiated power, the angular distribution of electric field or radiated power in the space in the far zone or in the far field region. That is what is called antenna parameter. That is what is called antenna radiation pattern. In the radiation pattern, we saw that there can be a main lobe. The pattern can be in different lobes. There can be a main lobe. Main lobe means it is a angular region in which maximum power is radiated. Most of the power is radiated in that angular region. That is the main lobe. Then there can be side lobes which are adjacent to the main lobe. So there will be a main lobe, then there will be a null, or there will be a zone where the power radiated or the field is very small, extremely small, or zero. It can be, if it is zero or extremely small compared to the main lobe, that is called a null. Then after the null, then there again can be another lobe which is smaller lobe where the power radiated is smaller compared to the power radiated in the main lobe region. Let me give you an example. Suppose we have an antenna. It is radiating in the direction, let us say, theta is equal to minus 30 degree to plus 30 degree. So that is the region, minus 30 degree to 30 degree. That is the region where maximum power is concentrated. Most of the power is radiated in that region. So suppose it is radiating 10 watt of power, then maybe 7 watt or 8 watt is radiated in this minus 30 degree to plus 30 degree region. Then from minus 30 degree to say minus 32 degree or minus 35 degree, this region there is almost no radiation, zero power. No power is in this region, minus 30 degree to minus 35 degree. Similarly, 30 degree to plus 35 degree, there is extremely low power. So you cannot receive, if you are in this range compared to the antenna, with respect to the antenna, you are in the angular range of plus 30 degree to plus 35 degree. There you do not receive any power. Or if you are in the minus 30 degree to minus 35 degree, you do not receive any power. So that range is called the null range, where we do not receive any power. Then we receive some amount of power from maybe minus 35 degree to minus 45 degree, or plus 35 degree to plus 45 degree. So though that angular zone where you receive again some power, so that zone is called the side lobe. Similarly, we saw there is back lobe. Then we saw what is side lobe level. The side lobe level is power radiated in the main lobe, a ratio of the power radiated in the side lobe by ratio of the power radiated in the main lobe. So main lobe, as I told you now, it may be 7-8 watts. Side lobe may be 2-3 watts, something like this. So this is about the lobes. Now, in terms of this, in terms of the radiation pattern, we can reference an antenna, or we can categorize an antenna in terms of its radiation pattern. When we do this, then we call it antenna referencing the antenna with respect to its radiation pattern. That is what is antenna referencing. So we will categorize the antenna according to the radiation produced by the antenna. For example, we have an isotropic antenna. By definition, isotropic antenna radiates in all directions equally. It is an hypothetical antenna. It does not exist in real world. So it is an ideal antenna, hypothetical antenna, or fictitious antenna. It radiates equally in all directions, and the radiation is constant. The radiation pattern is constant. So if you take the antenna at the center, then at any particular direction, at a distance of r, everywhere, if you draw a circle of radius r, everywhere on the perimeter of the circle, the power received will be same. That is what is. Or if you draw a sphere, everywhere on the surface of the sphere, the power received will be same when the antenna is at the center of the sphere. That is what is an isotropic antenna. So this is one category of antenna in terms of radiation pattern. So the radiation pattern is here spherical, so everywhere it is same, and this is called isotropic antenna. Similarly, there is another antenna which is called omnidirectional antenna. So these are a group of antenna, we can call them omnidirectional antenna. Example is an ideal dipole that we are going to study later. Ideal dipole is an example of omnidirectional antenna. Omnidirectional antenna, in this antenna, we consider one plane, usually the XY plane or the azimuth plane. XY plane is also called the azimuth plane. XY plane or the azimuth plane. We consider one plane. In that plane, we put the antenna at the origin, and we draw a circle of radius r. On the perimeter of the circle, everywhere the radiated power will be same. So pattern is constant in one plane along at a particular distance from antenna around a circle. So that is what is an omnidirectional antenna. This is physically realizable. This is not fictitious. This is physically realizable. This has many practical applications. We will consider some of the practical applications. One example is our cell phone. So when you are using cell phone, you are at your home. The cell phone tower may be at any direction from your home or from where you are using the cell phone in any angular. If you are at the center of a circle, on the circle, perimeter of the circle, at any angular point there can be a tower and you have to receive the signal. And therefore it is omnidirectional, because from everywhere you will receive the same amount of signal without any disturbance. So this is one antenna. Cell phone antennas, they should respond equally from all directions in the horizontal plane. Similarly, base station antenna, if the antenna is radiating, then it has to cover the area around it, completely around it. It cannot cover the area only in a particular direction. So it has to cover area around it. And therefore, base station antennas are also example of omnidirectional antenna. You cannot say that they are dipole and ideal dipole antenna, but they are omnidirectional antenna. So this is one part. Then we'll come to the other part. This look at a radiation pattern, a typical radiation pattern. You can see this type of radiation pattern is called a fan beam radiation pattern. Look at the main lobe that I am showing you here, that you can see the main lobe. The main lobe resembles the blade of a fan. Nowadays the fan blades have changed, but earlier when I was a child in those days, the fan blade shape was like this. Therefore, this type of beam is called a fan beam antenna. This beam is in the broadside direction. Broadside direction means antenna is in one plane, put the antenna in one plane, draw a perpendicular to that plane, and the radiation pattern is along that perpendicular. So the radiation pattern is perpendicular to that plane. If the radiation pattern is perpendicular to that plane, or the radiation pattern is normal to the plane containing the antenna, then that antenna is called broadside antenna. So this is a broadside antenna. Then the other type of antenna will be the end fire antenna. An example of this antenna is again ideal dipole. These are usually broadside antenna. The pattern is normal to the plane containing the antenna. Then comes the other type of antenna. Here you can see the second figure on the left hand side. The main lobe in the second figure is perpendicular to the main lobe in the first figure. So if the main lobe in the first figure is towards the z-axis, the main lobe in the second figure is along the x-axis or y-axis, or is on the xy plane. This type of antenna is called end fire array, end-to-end. Right. Here the main beam is in the plane containing the antenna. Broadside antenna, the main beam is normal to the plane containing the antenna. End fire antenna, and the main beam is in the plane containing the antenna. Since it is in the plane containing the antenna, therefore, if we have a linear current on the z-axis, a linear current on the z-axis means the antenna is along the z-axis, because the antenna element is the current element, and the current element is along z-axis. Therefore, antenna is along z-axis. If the antenna is along z-axis, then the broadside direction is theta is equal to 90 degree, and the end fire directions are theta is equal to 0 degree or 180 degree, or it can be 0 degree and 180 degree. So this is how you reference antenna, the end fire antenna, the broadside antenna. Other antennas are intermediate between the end fire antenna and broadside antenna. The middle figure shows you the radiation pattern which is intermediate between the end fire antenna and broadside antenna. Now let us come to the power radiated by antenna. The power is given by the pointing vector. As you know, pointing vector gives us power density. Therefore, the power is given by pointing vector. The pointing vector S, for time harmonic field, pointing vector S, and time average pointing vector S is equal to 1 by 2 E cross H conjugate, and its unit is watts per meter square. This we have studied. Pointing vector we have discussed. So S is equal to 1 by 2 E cross H conjugate, watts per meter square. Now, power flowing out through a core surface. Once we know what is pointing vector, we can find out the power flowing out through a core surface around the antenna. That will be P, which is equal to integration of the pointing vector, which is the power density. Since it is density, so we integrate it. Integration of the pointing vector over the surface enclosing the antenna. So, the power flowing out through a core surface will be P, which is equal to integration over a core surface ds of the pointing vector. Now, on the power radiated by the antenna, based on this power flowing out through a core surface, we can now define what will be the power radiated by the antenna. So that will be equal to, based on this power flowing out through the core surface, P is equal to 1 by 2 eta integration of E theta square plus E phi square r square d omega. So this integration d omega is over the solid angle. So infinitesimal solid angle is d omega. So total power radiated is equal to 1 by 2 eta into 1 by 2 eta, then integration of E theta square plus E phi square. Now you can ask me from where I am getting E theta square plus E phi square. That we get from this. S is equal to 1 by 2 E plus H. H is equal to E by eta. So put there E by eta. So S is equal to 1 by 2 into E cross E star by eta. That is 1 by 2 eta into E cross E star. So when you take the amplitude, then E into E star is equal to E square. E square is the amplitude. E is the vector. So amplitude of the vector, square of the amplitude of the vector is the square of the components of the vector. Now E vector has two components, E theta component and E phi component. Therefore E theta square plus E phi square. So that is E square. So that is what is S. So P is equal to 1 by 2 eta. Eta comes from H is equal to E star by eta. So from there you get eta. So 1 by 2 eta that comes. And then integration of E theta square plus E phi square. Then for ds is equal to r square d omega in terms of solid angle. The elemental surface area is r square d omega. R square into solid angle gives you the surface. So it is r square d omega is ds. Using that we get the power radiated by antenna. P is equal to 1 by 2 eta integration of E theta square plus E phi square into r square d omega. So this is about radiation power. Then next is radiation intensity. This is another power or another important characteristics of the antenna is radiation intensity. This is defined as the power radiated in a given direction per unit solid angle. This is the definition. Power radiated in a given direction. So direction will be fixed. So in that direction you want to find out how much power is radiated per unit solid angle in a given direction. Now what will be its unit? Unit will be, this is power radiated, so unit must be watt must be there. Then for solid angle is radian, steradian. So watts per steradian, that you can say unit will be watts per square radian or steradian. Steradian is also square radian. Advantage of this knowing the radiation intensity is that it is independent of the distance, because by the definition it is power radiated in a given direction, not at a distance, in a given direction per unit solid angle. So advantage is it is independent upon distance r. So you drop the distance r from here. Now we'll find out the expression for this. U theta phi, U is the radiation intensity. This comes from the power. So P is the power, P theta phi is the power. That expression we have already seen. Now we define U theta phi. This will be equal to 1 by 2 real part of power pointing vector. So pointing vector density is real part of E cross H conjugate, that into r square, r cap. So this is S theta phi r square. So find out the pointing vector, multiply that by r square. That gives you the U theta phi. So that we can write as U theta phi is equal to UM into F theta phi square. where f theta phi is the normalized power pattern. Sorry, f theta phi square is the normalized power pattern. F theta phi is the radiation pattern. F theta phi square is the normalized power pattern. Then you can, what is um? Um is the maximum value of u. So u theta max and phi max. It is not. It does not mean theta max. Phi max does not mean maximum value of theta and phi. U theta max is the maximum, the value of theta for which u is maximum. Phi max is the value of phi for which u is maximum. Therefore, um is equal to u theta max phi max. Then we can find out what is average radiation intensity. This is equal to the radiation intensity u that an isotropic source with the same input power P would radiate. That is what is called the average radiation intensity. So first you find out the radiation intensity of the antenna that is under consideration. Then consider an isotropic antenna with the same amount of power, same input power that we gave to the antenna under consideration. So same amount of power P is given to an isotropic radiator and the same amount of power is given to an practical antenna. Then the radiation intensity of the isotropic radiator is called the average radiation intensity. Analytically, you can say U average. U average is the radiation intensity, average radiation intensity. That will be 1 by 4 pi. From where we get 1 by 4 pi is very simple. It is the surface area of a unit circle, unit sphere. Unit sphere surface area will be 1 by 4 pi r square. R square is 1 unit sphere. So r is equal to 1. So from that you get 1 by 4 pi. So U average is equal to 1 by 4 pi integration over U theta phi d omega, omega being the solid angle. So that we can write integration of U theta phi d omega, that is equal to the total power that we have seen already. So since U theta phi d omega is the total power, so U average is equal to P by 4 pi. So that is what is average radiation intensity. So we have now found out expressions for radiation intensity. U theta P, which is equal to S into R square, or UM into F theta P square, or UM into F square. UM is the intensity, UM is the maximum intensity. Then we found out what is U average. Average radiation intensity is equal to P by 4. Then the next characteristics of the antenna is the directivity. Here you can see we have an antenna at the center, and if I replace the antenna with an isotropic antenna, then you can see that there is a circle. Dashed circle, that is the radiation pattern of an isotropic antenna, which is radiating same amount of power in all directions. Now, if I replace the isotropic antenna by this antenna, then you can see the amount of power that is enclosed within this circle or within this sphere is directed in a particular direction, which is towards the right side. Here you can see it is towards the right side. So that antenna, so it is directed, not uniform in all directions, but it has a particular direction. So the main beam is directed towards the right side, and it contains most of the power that was available for an isotropic antenna. So the directivity now is defined as the ratio of the radiation intensity in a reference direction to the average radiation intensity. Average radiation intensity is for an isotropic radiator, and the radiation intensity in a reference direction is the maximum direction. So by default, the reference direction is the maximum radiation direction, is the direction for maximum radiation. So D is equal to UM. UM is the maximum radiation intensity by U average. U average is the average radiation intensity. So directivity D is equal to UM by U average. So that we can write as UM by U average is P by 4 that we have seen. So it will be UM by P by 4. So this has no unit because U is intensity by intensity, same unit in the numerator denominator, so it becomes unitless. So D is equal to UM by P by 4. So we can write that as D is equal to UM by R divided by U average by R. So numerator and denominator will divide by R. So that gives us UM by R divided by P by 4 pi R. So numerator and denominator both we have divided by R. So from that we get UM by R divided by P by 4 pi R. So that is equivalent to power density at a distance R from the antenna. So directivity is equivalent to the power density at a distance R from the antenna. So this is another way of looking at it. Now let us do some physical interpretation of directivity. And this is, as we know, this is the ratio of maximum to average radiation intensities. By the definition we saw this. These are dimensionless. Ratio of maximum to average power densities, which have units of watts per meter square. So these are the two interpretations of these two D. D is equal to UM by U average, that is unitless, whereas D is equal to UM by R by U average by R, that is have units of watts per meter square. So this is basically a pictorial representation of the directivity. You can see on the left hand side the figure, and there is a right hand side figure. In the left hand side figure, it is the actual radiation pattern. On the right hand side figure, an actual radiation pattern contains maximum intensity UM and intensity is U. Same thing on the right hand side we are representing by a solid angle. In the solid angle, on the surface of the solid angle, the intensity is UM and the solid angle is omega A. So based on this, we define something called beam solid angle. The beam solid angle omega A is equal to surface integration of F square d omega, so that this will give us, it is the same solid angle as constant radiation of a level equal to the maximum value of radiation intensity over all the beam area. So we have seen the beam area, the left hand figure shows you the beam area. So from that we say that the solid angle, the solid is equivalent solid angle, the same solid angle as a constant radiation of a level. So radiation level is on the solid angle is equal to the maximum value of radiation intensity, which is UM. So a radiation level is equal to radiation level on the solid angle is equal to the maximum value of the radiation intensity over all beam area, that is the practical beam area or the actual pattern. So that way we can define P. P is equal to P the power is equal to UM. UM is the maximum radiation intensity then integration of f square d omega, that we can write as um into omega a. Omega a is the mean solid angle as we have defined it earlier. Then we can say u average is equal to p by 4 pi that we have defined earlier. Directivity d we defined as by u average, that we can write as by p by 4 pi because u average is equal to p by 4 pi. So that we can write as by p. For p we can write into omega a. So we write into omega a by 4 pi. Now in the numerator and denominator cancels out. So that gives us u average is equal to 4 pi by omega a. So this makes life easier. Instead of u average is equal to p by 4 pi, instead of finding the power etc., we can directly find out what is u average. It is equal to 4 pi by omega a. So the pattern shape determines the directivity. Simple. This shows us the pattern shape because it has omega a. So the pattern shape itself determines the directivity d. So d is equal to 4 pi by omega a pattern. So directivity is determined by the pattern shape. Now, directivity as a function of pattern angle is d theta phi. D now as a function of pattern angle theta phi will be d theta phi will be d into f square, where f is a function of theta phi. So d theta phi is defined as d into f theta phi square. And then we will come to the concept of directivity. This is simple. I have already told you. Let me explain it using a figure. We have a isotropic antenna or antenna whose power is same as the power of an isotropic antenna. So isotropic antenna, the intensity of radiation over a sphere will be u average. When the isotropic antenna is replaced by a practical antenna, and then look at the sphere, the radiation is along a direction which is crossing the sphere, which is crossing the radius of the sphere. And we have already seen is equal to d into u average. So it is crossing it, and the is more than u average by an amount of d, which is the directivity. D is the directivity. For the practical antenna is equal to d into u average. U average is the average intensity of an isotropic antenna. So it is more than the average intensity of the isotropic antenna by an amount d. So by an multiplying factor d. So d gives you the directivity. So and this is increase in the radiation intensity in the preferred direction in which the antenna is radiating. That is the preferred direction. In the preferred direction over that by an isotropic radiator of the same power. So this is the concept of directivity. Then we will come to the gain of the antenna. Gain of the antenna is 4 pi times the ratio of the maximum radiation intensity to the net power accepted by the antenna. So if you are giving some power P to the antenna, then it is 4 pi times the maximum radiation intensity. So 4 pi into um is the maximum radiation intensity. So 4 pi into divided by the PA. PA is the power accepted by the antenna. So this is how we define it, or P in. P in is the power input to the antenna. So 4 pi times the ratio of the maximum radiation intensity to the net power accepted by the antenna from the connected transmitter. That is what is the gain of the antenna. So maximum gain G is equal to 4 pi um divided by Pm. As a function of angle, if you want to represent it, then G theta phi is equal to F theta phi square. That is what is the gain as a function of angle. This is a power quantity, sometimes referred to as a power gain or power gain. There are different definitions of gain. You can look in the internet or look in the book. There is an IEEE gain, there is a standard gain. So there are different types of gain, but this gain is the gain that we are discussing is the most important one. This excludes impedance or polarization mismatch losses. What are these losses? That we will discuss towards the end of our lecture, today's lecture. I think we will take a break here. Then we will come back and discuss about other parts.